Hello friends, welcome to VK Lectures. In this lecture, we are discussing the phase space and phase space diagram from statistical mechanics, with very important concept in point of view of the competitive exams. So let's start with what is phase space. Now this phase space is talking about the position of the particle or the object and its position related to its momentum, and a plot or a graph between the position and momentum is nothing but the phase space diagram. And for example, we have the the momentum along the uh, y-axis, and on the x-axis we have the position. This is position, and here you have the momentum, and some trajectory it is following, and this is called the trajectory corresponding to the position. What is the momentum is what is given by the position momentum graph, and that is the trajectory. Now h, which is a Hamiltonian, will be a function of the position, that is q, and the momentum p. And in general you can also write it as Hamiltonian, which is a function of q, p, and t. And we know from the requisite from classical mechanics, the basic knowledge from classical mechanics, that is qi dot is equal to dou h by dou pi, and pi dot, that is nothing but the force. Pi, momentum, its time derivative is pi dot, so time derivative of momentum is force. That's given by minus dou h by dou qi. So this is from qi, which is a function of time, and here is a pi, which is again function of time. Now to understand more, let us consider a particle, a single particle in 3 dimension. The phase space, we will represent it by some diagram here. We'll take one of the cell here, so this is called one of the cell, and this is represented as this as space cell. And this is delta q, and here you have delta p, and delta q into delta p. So that is the uncertainty in position and the uncertainty in momentum, which we assume to be h at the maximum, the uncertainty. So h. Now similarly it will, since it is in 3 dimension, it will have qx, qy, and qz, or q1, q2, q3, or the position px, py, pz. This is just to represent the different dimensions. Okay. Similarly, we have, this is delta qx into delta px. So similarly, you have delta qy into delta py. We will get again h. This is x and this is y. Similarly, delta qz into delta pz is again h. So assuming this as a three-dimensional array, you can write the delta q into delta p will be equal to volume. You will have a volume, and that is equal to, this is h, this is again h, so h cube. So this becomes h cube delta q into delta p. So instead of this, we will have a three-dimensional array with qx, qy, and qz. Now that is for a particle, three-dimensional particle, and it will have 3 degrees of freedom. This degrees of freedom, 3 degrees of freedom, that is in the x direction, y direction, and z direction, and the dimension is 6. Dimension is like 6 because you have qx, qy, qz. This is qx for one particle. How many dimensions you need? For one particle, there is qx, qy, qz. Similarly, there is px, py, and pz. So for one particle, you require 6 dimensions. Okay. In 3D space. Now let us put this into n particle system. So this is just now what we have seen is for a single particle. Now for n particle with in 3 dimension, in degree of freedom being 3, let us see, there are q1x, q2x, q3x, etc. plus comma, and here you can write qnx. Right, now you have q1y, q2y, q3y, and qny. Similarly, q1z, q2z, q3z, and qnz. So here you get how many number? This is 3 dimension, so this corresponds to n. So there will be n number. This also n number, 1, 2, 3, etc. up to n. Again 1, 2, 3, etc. up to n. So you have 3n number of position coordinates. Similarly, you have p1x, p2x, etc. up to pnx, then p1y, p2y, etc. up to pny. Similarly, p1z, p2z, etc. up to pnz. And these also you will have 3n number of momentum coordinates, and together you will have 6 n coordinates. To describe an n particle system, you need 6 n coordinates. Now coming to the volume of the space cell. For a single space cell, you will have h cube. For a single space cell, you have h cube, and this is for single particle. For single particle, you had h cube, and for n particle system, for n particle, you will have h cube n. I mean h to the power 3n. This is because each dimension delta here, delta q1x into delta p1x into, so this is volume. Volume means into. So delta, this volume is not the volume of the, in general the volume, I mean it does not have the meter cube or volume of cell like liter. No, its dimension is not the dimension that we generally have. It is the volume of the space cell, which is made up of position and momentum coordinates. So delta q1x into delta p1x into delta q1y into delta p2y into delta q1z into delta p1z. So this goes on. Here now you have these three, then delta q2x into delta p2x, and it goes on. So it goes on, and the first three, this one, this gives h cube. So it goes on, the multiplication goes on for n times because you have n particles. So this gives us, for this is for single particle, and for n particles, so n particles, you have h to the power 3n, the volume of the space cell. To conclude, for an n particle system, so for n particle system with f degrees of freedom, of freedom, then dimension is what we have written the earlier time. Dimension is 2 times fn. Earlier it was f is 3, so 2 3, that is 6n. For then the volume of the phase space, so volume of phase space cell is h to the power f times n, h to the power e or nf. All right, so these are the two things in general what we can write. Now coming to the phase space once again. Phase space, qi dot is equal to dou h by dou p, while pi dot is equal to minus dou h by dou q. And the phase space diagram is something like this. You have on the y-axis, and this is on the x-axis x, this is p, or you can write it as q and p. So this is qi pi. So some trajectory it may show, and that is called phase space trajectory. So this is phase space trajectory. Now we will also write the Poisson bracket here. Poisson bracket for the two operators a, b. We can write it as sum over I dou a by dou qi into dou b by dou pi minus dou a by dou pi into dou b by dou qi. So this is a Poisson bracket for any operator a and b. Now from quantum mechanics we can write the equation of motion. Or with respect to the operator a, we want to know whether operator a is time independent, or how does operator a change with the values of, with the time. Okay, so d by dt of the expectation value of a is equal to 1 divided by I h cross the expectation value of the commutator of a comma h plus partial derivative of a with respect to time. So this is the quantum mechanical equations of motion, and in classical mechanics you will arrive at d by dt of a, the quantity a, is equal to Poisson bracket of a comma h plus dou by dou t, the partial derivative of the a. So this is in classical mechanics, while this is in quantum mechanics. Based on the concept of the equations of motion, the Liouville's theorem, Liouville's theorem. Now this is based on the previous concept, that is the equations of motion, and Liouville has given the equation of motion for the density. So d by dt, the rate of change of the density in classical mechanics, that it is with rho comma h, where h is the Hamiltonian, plus the partial derivative of the rho with respect to time, and this is equal to 0. Now what is the conclusion he has made is the rho is constant So since the time derivative, total time derivative of rho is 0, then rho must be a constant. So rho is constant, which means density of the phase space. Density remains constant. Yeah, this is with respect to time, and in phase space. Fine. So that was about Liouville's theorem, and this Liouville's theorem has got some uh, notes to make, or conclusions to make. That is, the motion of particle. The first one is the motion of particle in phase space is similar to or analogous to uh, motion of incompressible fluid. Fluid in real space. So that means in a pipe, if water is flowing, that is how the particle moves in a phase space. It cannot cross each other. The particle will follow the straight path like this. I mean, similar path. They do not cross each other. They will be that is called streamlined motion. Streamlined motion. Now this also gives the idea that the trajectory of every particle, trajectory means trajectory in the phase space, is well defined. It cannot be moving very randomly. It has to be well defined. And it also makes another conclusion that no two trajectories can intersect each other. Okay, so that is how the streamlined motion is also there. Every particle will be following the certain path, and it has to be remaining in that particular position. Okay, so for example, one particle moves here and another particle. So after flow of the one particle in this direction, the next particle, if it touches this point, it will also go through the same path. Okay, so every particle has its own trajectory. Here is one question regarding the phase space trajectory. Now the question is, which of the following trajectories are not possible for a particle obeying Hamilton equation of motion? Now take the case of the first one. Here it is not intersecting. The phase space trajectories for this is for two particles, so one or two different energies, but usually it is for two different particles. So so this one is different. I mean, they do not intersect, so this is possible trajectory. Now here in this case there is one trajectory going in from one point to the another, and another is uh, another trajectory. It is having the intersecting at 2 points, so this is not possible. Here the trajectory is going above the another trajectory. This is obviously it is possible, so third one is okay. And this is uh, elliptical one. This is not intersecting at any point, they are all distinct. Usually this represent the trajectories with the different energies for a single particle, but for different particles also can be given, so it is also possible. Now here the trajectories are intersecting, or the single trajectory is intersecting at 3 different points, so this is also not possible. So here this is the second one, third, fourth and fifth. So here second and fifth one not possible because they intersect. Phase space trajectory. So phase space trajectory is a graph or a plot. So it's a plot or a graph. Now between who and who, it is between the position Q and the momentum P. So between position and momentum, the plot is called the phase space trajectory. And to understand this, let us take the simple case of one-dimensional box. So particle in one-dimensional box is a free particle, and it is moving between two rigid walls. Moving between two rigid walls. The rigid wall indicates that high potential barrier or infinite potential barrier. That means the particle cannot penetrate and go outside. So that's called one-dimensional box. Now the Hamiltonian of the 1D box, that is the total energy, that is the kinetic energy plus the potential energy, that is given by P square by 2m, which will be the kinetic energy, but the 1D box potential energy is 0, because if you consider this as the 1D box of length 0 to L, this is infinite potential, here is infinite potential, and the potential inside is 0 and the particle is here, so the particle is having 0 potential. So it's the total Hamiltonian is H is equal to P square by 2m. Okay. Now from this is the total energy. So total energy is equal to, there will be only kinetic energy because potential energy is 0, so P square divided by 2m. Now this indicates P square is equal to 2me, and P is equal to plus or minus root of 2me. Now this indicates that P is constant because 2 is constant, em is constant, and total energy of the particle remains constant. So here we can write the P as constant. So how the trajectory look like? So this is the P, that is the momentum, and this is our x-axis, x-axis, where you write the position Q. Now up to here we have the length of the box. This is the 0, so length of the box is up to here, but we know that the p value is ranging from plus root of 2me to minus root of 2me. So this is the plus root 2me, while the same point towards the negative direction you have minus root of 2me, and from here it is constant up to the length L. Here it is constant up to the length L. So this is the phase space diagram for one-dimensional box. So you can write the trajectory for one-dimensional box is this. You can write it as a rectangle. So 1D box phase space trajectory is rectangle. For the further understanding, we can do one more system, that is linear harmonic oscillator. LHO, linear harmonic oscillator, which executes simple harmonic motion. One good example of simple harmonic motion is spring and mass system. Spring mass system, where a mass is attached to a rigid boundary over a spring. So this is M as the mass, and this is the equilibrium point, x equal to 0, and simple harmonic motion or linear harmonic oscillator oscillates about a stable equilibrium point. Oscillates about a stable equilibrium point. Stable equilibrium point. So this spring mass system, this mass is executing simple harmonic motion about x equal to 0, and if there is an external force in this positive x direction, then there is a velocity which is developed in the opposite direction. So force is equal to minus k times x, which means this is the actually the force is in the opposite direction, that is in induced force. That means if the we can forget about this term now, force here. So force, when you drag this mass to a certain point after x equal to 0, there is an induced force in this opposite direction. So that is equal to, that force is equal to minus k times x. And similarly velocity is in this direction. So if velocity is in this direction, momentum will be also in the same direction. So when x is positive, that is x is positive, when x is positive, the momentum p is negative. That means when you push the x towards the positive direction, the momentum developed will be in the negative direction. Now let us understand about the total energy of the system. Total energy E is equal to the kinetic energy plus the potential energy. Now the kinetic energy is half mv square plus half kx square. So just writing it in terms of momentum, p square by 2m plus half kx squared. So this is the total energy of the system E. Now let us divide the equation 1 by the total energy E. So what we achieve is 1 is equal to divide the entire system, so p square by 2m E plus half kx squared by E. So let us write down as it is x square by E. Now just rearranging this, p square by 2m E plus half k by, so x square divided by 2e by k. So this is this is the equation. Now it's equal to 1. Now what we can do is 1 is equal to p square divided by root of 2me whole squared plus x square divided by root of 2e by k whole squared. Now this is of the form x square by a square plus y square by b square equal to 1. This is the ellipse equation. Now this is the ellipse equation, and we know we need to find now what are a and b. So now we have this is x square by x square divided by root of 2e by k whole squared plus p square, that is our on the y-axis, root of 2m e whole squared equal to 1. So this gives us a, the value of a is equal to root of 2e by k, and b is equal to root of 2m e. Now this a is the semi-major axis and this is semi-minor axis. Now what is that? Now the area of the ellipse given by pi EAB, so that's equal to, area is equal to pi times root of 2m e into root of 2e by k root 0. So that's equal to pi times root of 2m e square divided by k, that's equal to pi root of 2m by k into e. So that's the area. Now let us find the trajectory. So trajectory is, as we discussed, it is a ellipse So we know this is an ellipse. So this is the B, and here you have A, which is the semi-major axis, and B, semi-minor axis. The values of A and B have been found. Now this is the phase space trajectory, which is an ellipse. Now we need to understand the direction of the movement of trajectory, and this is from point A. Now this is due to, we know that when x is positive, p is negative. So that means when x is moving in the positive direction, that is in this direction, p should be moving in this direction. That means towards the opposite direction. So it has to be the clockwise direction. So it is the direction of phase space trajectory for linear harmonic oscillator.